Hello everyone, my name is Sansevero. I'm currently a senior at the University of Michigan studying engineering physics, and I currently work in Professor Sarapotti's research group as an MTV undergraduate fellow. The focus of my presentation is the study of fission correlations, and these correlations are a key area of study for the empirical validation of nuclear models used in fission simulations and event generators, which are important tools related to the science of nonproliferation and security. So the specific correlations that we study are neutron-photon multiplicity correlations, which have been pretty well characterized in the past, and it has been shown that there's a negative correlation between the multiplicities of neutrons and photons. However, the dependence of this correlation on quantities such as particle energy and angles has yet to be fully characterized. In this presentation, I'll discuss how we extract the energy and angular dependence of this multiplicity correlation from experimental data taken at the Kainu system at Los Alamos National Laboratory. The fission data was collected on an event-by-event basis, and the Kainu system is a hemispherical array with a 1 meter radius. It consists of 3 fission chambers used to tag fissions and 42 liquid organic scintillators capable of PSD for neutron and gamma detection. So in order to get this angular dependence, we look at the angle between the emitted neutron and the photon. And to get this angle, we use the angles between the detectors that the particles were detected in. And so what this top left plot shows on the left is basically each point in the top half of the plot is a detector pair in the Kainu array, and the radial distance is the doubles efficiency of that detector pair, and the angle from the horizontal is the angle between the detectors in each pair. And so if we bin these together into angular bins, we get the bottom half of the plot, which essentially qualitatively shows by the size of the circles, like how many detectors make a certain angle, or how many detector pairs we have in the system that make a specific angle in each bin. And so on the right-hand side, what we have is the neutron-photon multiplicity correlation as it varies with the angle between the emitted particles. And just to clarify, this is the angle between the neutron and the photon, and not with respect to the fission axis. And typically, Legendre polynomials are used for describing angular emissions with respect to the fission axis, and even though this is not the angle that we're using here, we do use Legendre polynomials to fit the data. And our justification for that is that essentially, particularly for high neutron energies, neutron emission is biased in the direction of the fission axis in the lab frame due to fragment kinematics. And so the angle between the neutron and the photon is essentially the angle that the photon makes with respect to a cone of emitted neutrons around the fission axis. And so we thought the Legendre polynomials would be a good way to fit the data. What we see in the plot is that this multiplicity correlation is strongest when the neutron and photon make a 90-degree angle with each other. And we see that the overall correlation, average over all the angle bins, is negative, which is in agreement with previous measurements. In order to introduce the next layer of dependence, we can discriminate the particles based on their energies. For neutrons, we obtain their energies via time of flight, and for photons, we use the energy deposited in terms of the light output in the scintillator. We are currently working on unfolding these energies in order to get a dependence on the emitted particle energies, but for now, we are working with these methods right here. Essentially, what we do is obtain a plot like the one on the top right for different energy regions for neutrons and photons. And then we can compare the fits of the plot, the parameters of the fits of the plot, in order to make a qualitative description of these distributions in different energy regions. So the first parameter essentially dictates the vertical shift of the distribution and is essentially a measure of the multiplicity correlation averaged over all the angles. And interestingly, we can see that the multiplicity correlation is negative for regions of low neutron energy, but it switches sign in the regions of high neutron and high photon energies. The behavior and structure in this energy dependence was detailed in Stefano Marin's talk yesterday. And so we also see in the low neutron energy region, the multiplicity correlation becomes stronger with gamma energy. And we can interpret this as an indication that high energy photons compete more with neutrons than low energy photons. The second parameter qualitatively describes the curvature of the distribution, and in this experimental context, this parameter can be interpreted as the anisotropy of the gammas with respect to the cone of neutrons emitted around the fission axis. What we observe is a change in sign at high photon energies. Overall, these results illustrate some interesting behavior that provoke further questions about what this statistical behavior can tell us about neutron and gamma dependence on fragment characteristics like angular momentum and excitation energy. For example, closely related investigations have studied the dependence of gamma emission on the angle it makes with respect to the fission axis, and these studies predict different angular distributions for each of the multiple radiations. In comparison to our experimental approach, if we characterize the gamma fission axis angle as the high energy limit of the gamma neutron angle, we see an interesting result in the gamma anisotropy at high energies. The majority of the regions show a positive curvature, corresponding most likely to quadruple contributions. However, specific gamma energies, the curvature of the angular distribution switches sign, and this is a surprising result that begs further investigation. So the next steps that we plan to take in the future are to unfold these detected energies to more accurately represent the true statistics of the emitted particles, and further we hope to find more rigorous justifications for the statistical behavior by connecting these correlations to physical predictions based on fission fragment observables. I would like to close by thanking the MTV for the opportunity to participate in this research. And as an undergraduate student, it has been personally very challenging and very rewarding experience. And over the course of my research, I've been able to develop and learn many, many new skills and ways of thinking in relation to scientific research. Thank you all for listening, and have a good day.